Why'd you erase that?
Well, because I really wanted it to reflect off of this layer. Because it's really this middle layer that is reflective. So hopefully that'll help. First question for you. The light bulb is an incoherent source. Oh, yeah. Thank you. Speaking of someone not operating on much sleep, right? Although I have no excuse for it. I celebrated last night. Got my exam done last time. Okay, so there we go. Some questions to ponder. Ponder got cut off. And there, come on. Oh, there we go. To ponder. The light source is, wow, that's weird. The light source is incoherent. So why would a photon traveling down the fixed arm interfere with one on the moving arm? Because we know conceptually that it is the interference between, it's the interference that results in the interferogram, which we will Fourier transform to generate the spectrum. I'm assuming that that's sort of some baseline knowledge that I don't have to go through. And we can just sort of jump into the puzzling details thereof. So are you pondering? Any ideas? Yeah. Yes. So in this schematic, yes, the variable mirror moves, and then so the path length between these two arms differs, and as a result, we see interference at the detector for a monochromatic source. But why is a photon that travels to this arm interfering with a photon that travels down the other arm? Well, yeah, but it's random phase. So it's not like a laser where everything is phase coherent. This is just a light bulb. I stumped you on the first question? Yes, they are traveling different distances. But why would they interfere? Because you've got a photon that's going this way and another photon that's going the other way. Why would they have to have some sort of phase relationship with each other? You're getting close. Yeah, I misled you by bringing in the idea of the photon. Because if you think about it, if you have a wave that's coming from this source, let's just imagine this is a wave. Then half of the wave goes this way, half of the wave goes the other way, and then they come back and interfere at your detector. So each photon is interfering with itself, and each photon travels down both paths in the interferometer. Huh? It's a wave. It's not a particle. So if it's a wave, then that photon can go both ways, and until somebody asks it where it is, it's both places. Quantum mechanics is awesome, right? But really, the hardest part about quantum mechanics is this whole idea of a particle that just gets in the way of understanding everything about quantum mechanics, in which everything you need for quantum mechanics can be described entirely by abandoning the notion of a particle and accepting the fact that matter is completely described by a wave. But I digress. A photon is just one example thereof in this particular case. Does it make sense that that the wave of a photon is traveling both arms and interferes with itself? And as soon as I say that, then, yeah, makes sense. All on the same page. Okay, let's ask another question then, too. If the photon is destructively interfering, where did it go? destructively interfering at the detector. Where did it go? Have we annihilated matter? Energy must be conserved somehow. What happened to the photon?
It's still there, it's just we're not measuring it anymore.
It has zero amplitude at the detector. So no, it's not there. Yes! It's an interference effect. So if it's destructively interfering at the sample, it must be constructively interfering somewhere else. Where? And I said if it's destructively interfering at the detector, then it must be constructively interfering somewhere else. Given this schematic, where is it constructively interfering? At the source. Right? Because it's a 50-50 beam splitter. So if you have destructive interference on this arm, you must have constructive interference on this arm and vice versa. Because there's a sign change upon reflectivity. Maybe that makes sense. Maybe it doesn't. But I see people sort of pondering this. I should let that soak in before moving on to the next point? Or should I keep rolling? Keep rolling? Okay. Oh yeah, this is a good one. 3. What dictates spectral resolution in an FTIR? Any other ideas? The airy disk? Oh, the wavelength of light? Or yes, spectral. Okay, so we'll yeah. Not the wavelength of light. Yeah. Distance traveled. Any other ideas? Turns out to be this one, and not the step size of the mirror. Do we have an understanding as to why? Yes. Hopefully. Otherwise, why would I bring it up, right? Delta T, delta nu, greater than or equal to 1, right? Delta X, delta nu bar, greater than or equal to 1. Nu bar is wave numbers. Delta X is distance traveled. If we travel a greater distance, then we have less uncertainty in the wavelength. Now, conceptually, why does that make sense? So, mathematically, great. Understand it, sure, sort of. Maybe not. Not really. Don't know what's going on. But conceptually, let's see if we can sort of rationalize this. So let's ask what would happen at the detector for 3 different wavelengths, all shining at the detector simultaneously as we scan the mirror. So we're going to have something that looks like intensity versus Xi, right? And it's going to look like right? If I have one wavelength, it's just going to oscillate. We'll see why mathematically later on, but conceptually, if I have a single monochromatic light source and I'm shining it on the detector, and as I'm translating, it's just shifting itself back another wavelength, and so it's just going to keep recurring in oscillations, just like on the exam, with your repeating exponential. Or if you look at this autocorrelogram over time, it will just keep repeating, and so on, right? Now, if we add another wavelength, that's close but slightly higher in energy, and then we add another wavelength, it's close. Oops. And slightly longer in energy. As soon as these energy differences get closer and closer, we're going to have to move out further and further in x in order to get them to resolve. Does that make sense conceptually now? And all this is again, delta x, delta nu bar. Nu bar is the wave number. So these have units of distance. Units of 1 over distance is greater than or equal to 1, just like the Heisenberg uncertainty principle. So that's what dictates spectral resolution in an FTIR. Okay. I need my schematic. I'm going to try and reproduce it. It's going to be, I'm going to do it really fast, so that way it'll be a really crappy job. But let's go ahead and try anyway, because I want to add in a couple more elements. There's the mirror. I've got my light source. I'll have it go to here and add another. So source detector sample, movable mirror, fixed mirror, interferometer, right? What you will often find are 2 additional light sources that are in just about every commercial FTIR. We always talk about the infrared, but there's also typically 2. Another one is a Heaney. Which goes to a detector. And another is a white light source. Just another light bulb at a hotter temperature. And that comes down and does the same thing. So what's the difference between the Heaney and the infrared source? Well, the Heaney it's a gas laser. So what are the characteristics of gas lasers? Well, the nice thing about gases is that every atom is essentially identical. So you have no inhomogeneous broadening, and you have nice narrow lines spectrally. So the Heaney has a wavelength of 632.8 nanometers. And in fact, you could even throw in a couple more significant figures if you really want to. Nice narrow band. So the question I have for you is, why does adding the Heaney help tell you the position of the mirror? Yeah?
It has a fixed wavelength that calculates from the interference that you're getting on Ftir.
So if I can paraphrase, if you imagine I think I'm going to paraphrase, but I'm going to do it in a questioning way. So what is the intensity going to look like on that detector as you translate the mirror? If this is monochromatic light, there's no true thing as truly monochromatic light, but this approaches it because it's narrow band. Yeah, it'll be just like the red trace alone. It'll just oscillate forever. Why is that advantageous here? How can that be used to measure distance? Well, if I have a wavelength of 632.8, then what's the distance between here and here? It's 632.8 over 2 nanometers. 2, because you're traveling there and back. So the overall increase in path length for the movable arm is twice that distance, if that makes sense. And then, so we have a ruler that, based on intensity, gives us a precision in position within 300 nanometers. Every time we have it on the maximum, we know we've traveled 300 and something nanometers, 315 nanometers, basically. And that's hard to do. I mean, optical methods are really nice for precise positioning for this very reason. So we use the Heaney as, I'm going to change colors again here. Heaney provides an accurate measure of distance, measure of displacement. Slick, huh? And that's all basically autocorrelogram, right? You're interfering the same thing with itself, and the autocorrelogram gives you that oscillating cosine, which tells you how far you stepped. What about the white light source? Why use that? What's that going to look like in the Fourier domain? As we vary the lengths of the two arms, what are we going to expect to see in the white light arm? In the white light detector channel as a function of displacement, and why does that help us?
Does it help you get rid of, it's like a baseline?
Not really.
Is this an ideal white light source where it's getting all?
Yeah. But so it's also an ideal infrared source. So. The infrared is like, what does the interferogram look like for the infrared? In other words, if I have a broadband infrared source and I'm shining it on the detector, what am I measuring here as a function of this displacement for the infrared? Let's do that one first, and then we'll get a sense of what the visible looks like and how it's different. I'll give you a hint. What would the sum of these three things look like? Well, it would have a maximum here, right? And then the more wavelengths you have, the more it'll damp out. And so you'll have something that'll look like that. Oh, it's symmetric. And my artistry is terrible. So imagine that being symmetric as opposed to what I actually drew. Okay. So why would adding a white light source help? Well, if I went from infrared to white light, how would this interferogram change qualitatively? The wavelength would change. So how would a shorter wavelength affect this interferogram? Well, it's symmetric. It would make it a lot narrower. Exactly. So this would be for the infrared. If I did it for the visible, it would look like that on the same scale, because it's just a much shorter wavelength, right? By at least an order of magnitude. Okay. Why do that? Seems like a waste, right? What might complicate? Okay, so we used an optical beam to determine the displacement of Xi. And we did that because we could do it more precisely. So that gives us, every time we move the mirror, we know what additional step that has gone. But in order to do the FFT of that, what other piece of information do we need to know? Instead of just the scaling on the x-axis, what other information do we need? The phase, the origin. We need to know where 0 is. Right? And if you look at this, it's going to really nicely give you this interference and only at the position when those two mirrors are exactly identical. So that then gives you an absolute scale of where equidistant position is on the mirrors. Because you can't rely, if you want to get this within a few nanometers, you can't rely on mechanics. You just have to measure it and then do everything associated relative to that position. Yeah? Yeah, cool stuff, huh? Okay, I'm excited about it. Maybe you guys aren't. So let's do a little bit of math. Throw some math at this. It's kind of fun that way. We'll take advantage of our Fourier transforms and see if we can understand mathematically what's going on in the Fourier transform FTIR spectrometer, and how what we measure relates back to the tools that we've developed through Fourier transform manipulations. So if we go back to that schematic for the interferometer shown up over here. Well, actually, I have it over here too. I'll put it up on both screens that way. So if we just consider the infrared beam path now, for a monochromatic wave, just one wavelength out of this white light source, we'll do it one wavelength at a time and ask what's going to be detected here. For a single wavelength. What we're going to be measuring is if we measure what's the electric field, we'll do electric field first and then intensity. The electric field at the detector as a function of this distance c, assuming we have it all calibrated, reference to 0, and know exactly what that distance is now by combining the white light and the Heaney information. Then this is going to equal, we have half the light on average reaching our detector, right? So that'll be 1/2 cosine 2 pi nu bar x plus 1/2 cosine 2 pi nu bar x plus c. Right? That's the electric field. Yes? Okay, yeah. That's the electric field at the detector for a monochromatic source. One of the many wavelengths that are contained within the manifold from the source. Okay, what's the intensity what's the time averaged intensity at the detector? Well, it's a little awkward to ask because we're expressing this not in terms of f and t, but in terms of x and nu bar. But let's ask ourselves, what would it be? The intensity averaged is going to be, it'll be the integral of E star E dt. Right? But we have this E expressed as a function of x and c and not as a function of t. So how do we get around that? Well, it turns out there's a really useful relationship converting distance to time when it comes to light. C equals, this is x, well, let's see, x lambda over, let's see, meters per second over frequency. So if we want to convert from, lambda nu. There we go. That's what I meant. I knew there was a nu in there somewhere. Not an h nu, but a lambda nu. That was close when I first wrote it down. H nu, it just sort of naturally, E equals h nu, C equals lambda nu. Okay. So we can use the speed of light to convert from a time average to a distance average. In other words, if I have a 10 microsecond integration time, that corresponds to what distance? Well, that's going to be the distance that light travels in 10 microseconds. Delta x is distance that's going to be 3 times 10 to the 8 meters per second times 10 to the minus 5 seconds. A lot of meters. Lots. Especially when you bear in mind that the wavelength of light is on the order of a micron in the infrared, and we're traveling something like 3,000 meters. You know, that's how long we're integrating. If we were to take and stretch that 10 microsecond pulse out and say how long is the corresponding photon, or the corresponding time of a light hitting it, given the speed of light, that would be 3 kilometers. Yeah, 3 kilometers relative to a micron. A lot of oscillations. Is that making sense to people? Okay. So so this becomes then equivalently 0 to x0, and in fact, I'm just going to rewrite this. I'm going to say that I, as a function of xi, is going to be the limit of that. Where I'm assuming that infinity is pretty close to what we're actually talking about, because 3 kilometers is a lot longer than the actual wavelength of light, and so it's effectively infinity. Yeah? Cool. Okay. So what's E star E? Well, I have E. I've written it down before. That's going to be cosine. I have a factor of 1/4 here. I'll pull out. I have a 1/2 times 1/2. So that'll be cosine of 2 pi nu bar x plus cosine 2 pi nu bar x. I'll start over on this. Nu bar. I keep wanting to put that parentheses in there. Nu bar x plus xi squared dx. Yeah? Okay. So if I FOIL this thing out, first, outer, inner, last, there we go. Knew it would come to me eventually. You're going to have a 1/4 times 1 over x0. This is still a limit. Integral from 0 to x0 of cosine squared 2 pi nu bar x dx plus 1 over x0 integral 0 to x0 cosine squared 2 pi nu bar x plus xi dx plus 2 1 over x0 integral 0 to infinity, well, x0, sorry. We're going to take the limit as that approaches it. Cosine 2 pi nu bar x times cosine 2 pi nu bar x plus xi dx. Close brackets. Let's look at that first one first. What does that do? Well, actually, that do in the limit of x0 approaching infinity. Well, we have cosine squared, right? So what's the time average, or in this case, distanced averaged value of that function? It's cosine squared, so it's 1/2, right? In fact, we can think of this, if we just do cosine squared as 1/2 plus 1/2 cosine 2x, then we know that the time average of the 2x time goes to 0, and we have 1/2. Maybe that helps, maybe it doesn't. Conceptually, you can look at this and sort of guess that it should be 1/2, and that's exactly what it does equal. What about this next one? what's different from this? I have the exact same thing, I'm just shifting it over by this factor of c. So the phase shifted, otherwise identical. So what's the average value of that going to be? Same. Yeah? And then we get to the interesting one. And I need an interesting color. Ooh, boy. How about purple? We hardly ever use purple. What about that one? Where have we seen something that looks like that? Yeah, it looks kind of like a Fourier transform, or the convolution, but in fact, the sign is consistent with autocorrelation and not convolution. So this is, it's exactly like it, right? It's the same thing, just added with a shift, and you're integrating it. This is an autocorrelation. And that kind of makes sense intuitively as well, that what we would be detecting in intensity would be the autocorrelation of the signal with itself in this interferometer configuration. Yay! Fourier transform. Okay, so if I summarize all of this, hopefully I can get this right. Please double check me. What I have is 1/4 times 1/2 plus 1/2, 1/12. How did that happen? 1/2 plus 2/2. Oh, I haven't done the 2 part yet there. Okay. Plus 2 times that integral. Do I want to just rewrite the integral? Sure. We'll do it completely here. 1/x0 integral 0 to x0 of cosine 2 pi nu bar x times cosine 2 pi nu bar x plus c dx. Yeah? Okay. Turns out we solved this one before, from back in the day. Cosine A times cosine B, if they're different, you end up with 1/2 cosine A plus B plus 1/2 cosine A minus B. Yeah? You're never allowed to forget anything that you hear in this room. That's the expectation as an instructor, that if I say it, there is perfect retention. That's true for every instructor, in fact. That's just a simple expectation. It's just the nature of the job. All right. So if you remember this, that's fantastic. If not, it's okay. I forgive you this time. Okay, so if I do the sum and difference of whatever is inside these two cosines, what do you get? I'll have 1/4 1 plus 2 over 2 times 1/x0 integral of, the first one, I'll have another factor of 1/2 here, so I'll pull out that 1/2. Hopefully everyone, this factor of 1/2, I'm just putting here. And I've got the sum, which will be cosine of 2 pi nu bar 2x plus c. Plus, we'll do a whole another separate integral here. 1/x0 integral 0 to x0 of cosine 2 pi nu bar c dx. Two integrals there. Yeah. Does everyone see what I did? Hopefully that's nothing too underhanded. I can be underhanded. Not intentionally, usually.
Is there supposed to be a plus in that first cosine thing?
Yes, what I did was I added x plus c to make 2x plus c. Oh, yeah. That looked weird, so I erased it, but I should probably have it there. Yeah. All good? Yeah, sure, why not? Let's just get on with the things, huh? Come on. This isn't going to be on the exam. Okay. This first term looks just like the one that we solved previously, except it's not cosine squared. It's just plain cosine. So what's the time averaged, or in this case, distanced averaged value of cosine of something time of x of 2x? Let's write it out. Cosine. It's phase shifted. I've left out the phase shift, but it has it's shorter period, 2x instead of x, but it's just oscillating about 0. So the time average goes away. And then I ask, look at this integral. Is what's inside that integral a function of x? No. It can be pulled out. And then I've got 1 over x, integral 0 to x0 dx. That's 1. Do you want me to pull it out explicitly? No? You don't need me to. Excellent. Last day. Why bother with such menial tripe? All right, so we can take this whole thing here, pull it out, and we're left with 1/4, 1 plus cosine 2 pi nu bar c. And what does that look like? This is in the C domain. It's going to look like that. Cosine, centered about 0. With an offset, 1 plus cosine. And it'll go up to a total of 1/4. What's the Fourier transform? Oh, come on, you guys have to know the Fourier transform of cosine by this point. Even double delta, right? So in the frequency domain, I'm sorry, in frequency nu bar domain, an even double impulse. At nu bar and negative nu bar. Now, because we've done autocorrelation, we know that the function itself must ultimately necessarily be symmetric. So there's really just redundant information here. In its redundant sense, phi of nu bar is symmetric. So therefore, I'm sorry, phi of f of t, f of x is symmetric, so therefore phi of nu bar is also even. And so if you plot a spectrum, there's really no point in including the negative frequencies because they yield no additional information. And so this is your FTIR spectrum. Why does it look like just a sharp line? Yeah. So we're worked this whole thing through for one wavelength. Right? And so for monochromatic light, well, yeah, in the Fourier domain, you should just have a nice peak at this particular nu bar. And so you can imagine if you have something that is not monochromatic, you'll get you can just repeat this procedure conceptually for every individual wavelength and generate a spectrum. Cool stuff, huh? No love for FTR. Okay. So that was the math, the Fourier transform math. The next thing I wanted to chat about. Are you heading out to the liquor store?
Yeah.
Yep.
Are we going to do it here or?
Oh, in the office. Part of celebration. You know, part of the reason for doing it in front of the office is that there's a pretty firm policy on alcoholic beverages on campuses, and so I really don't think it would be appropriate to celebrate with anything that someone might bring. in a classroom. Okay. Oh, there is no next time. NMR. In a big magnetic field, you're going to generate, you're going to align all the molecular atomic dipoles along the field. Not all, a very small fraction. Align a small population. Actually, it'd be anti-parallel. So in a large static electric field, the atomic dipoles orient the opposite direction. Now, how do we do spectroscopy with this? The answer is we can't. So what do you do? How many people have studied NMR in undergraduate? Yeah, some people even now. What do you do with this system? Well, right now it's just sitting there, right? Oh, so one way to do this would be to turn off B0. Turns out that's like, see, imagine in the NMR spectrometer you just move the magnets away really fast. And then measure this dipole slowly decay. Unfortunately, it's not dynamic, right? They're just sitting there. So, in other words, these atomic dipoles are aligned. So I have one macroscopic magnetization in the sample that is co-parallel with B0. But that's just a constant in time. So what do you do? Yeah! You pulse in a radio frequency to get them to reorient. And the way that we conceptually view this is that you tilt it this way. And I hate that because it makes no sense to me in my mind at all. And so what I did was I think you need a demo for these things. And the only way to really understand magnetic dipoles is to think in terms of angular momentum, right? Because it's electric charge that oscillates that generates the magnetic dipole. So if I've got, you see all sorts of really cool things with angular momentum. If I want to apply a pulse to rotate this, then I push this way to rotate it this way. Does that make sense? So the way that you push is different. And if I'm pushing up to the ceiling, it's rotating in the orthogonal direction, which is kind of funky and hurts your arms if you're not careful. So that's just one sort of interesting note in terms of how I want to orient this. So if I push in one direction, it's going to actually rotate that magnetization in the other. So if I'm starting out with B0 pointing toward that wall, and I want something to measure, then one option would be to rotate this so that the magnetization is now pointing in an orthogonal axis, and now it's a little bit easier to measure, but it doesn't carry any really interesting information with it, right? So what's the key to make this do something that's resonant? Wiggle.
Wiggle it.
Yeah. I need a little more speed here. So this is, if there's time, and if you have inclination, I can tell you when I wiggle this, I can't wiggle it at any frequency I want. I have to wiggle it at the resonant frequency. This is the only frequency that can get an amplitude increase in this precessional motion. Now, what is the dipole doing if I'm thinking along the axis here, the dipole sitting here? What is the dipole doing as I'm undergoing precessional motion? It's now, it's now sweeping out a cone. And if I make this bigger, ow, that hurts. If I make it bigger and bigger, I hurt myself. But you can imagine the thing actually precessing in the sense that it is now going to be looking like this. It's going to get a large enough amplitude of precessional motion, it's now going to be spinning. Yeah? What's the advantage of this? Now I have a dipole that is spinning around orthogonal to B0. And because these precessional frequencies are characteristic of the individual atoms, it allows you to separate them out. And so the idea is you just put a coil here. If B0 is applied in and out of the screen, then you can apply a current through one coil to get it to orient, and then measure the current that gets through the other coil. So when the magnetization swings around and points this way, then we have a current that goes this way. When it swings around and goes the other way, then we have a current that goes the other way. So there's a current that's going to oscillate in this coil as this thing is spinning around. And it's a pi/2 pulse that activates this, right? In the standard simplest measurement, you've got something sitting here, everything nice and aligned, and then you apply a pi/2 pulse. And what that does is result in this precessional motion that makes them spin this way. It starts them out all at the same time, and then there's a free induction decay. Yeah? Okay. You really do need to feel it. If you get that thing going, you really can't tell. There's only one precessional frequency of my bicycle wheel. And it's just like that same thing for all atoms, which is where you get that specificity for wheels. I mean, atoms. Okay. Oh, come on. I need more space.
If you are spinning the wheel at a different speed, does that affect the resonant frequency?
Yeah. The question is, if I change the speed of spinning, does it affect the resonant frequency? I don't know. I think it probably must. Yeah, it must. Feels like it should. But of course, nuclei, you can't speed them up or slow them down. They do what they're going to do. There is no next time. It's sad, isn't it? It's bittersweet. This time we've spent together has been special for me. Okay. Really, really special. Okay, so the idea is that you come in with a pulse. And then it reorients these dipoles, and so you end up with something that does a free induction decay. There's my free induction decay. So if you have however many megahertz spectrometer, 800 megahertz, let's go high end spectrometer. What are the units of the horizontal axis in an NMR spectrum? ppm. So if I have an 800 megahertz spectrometer, then my range here is in parts per million is going to go out to 800 hertz. What that also means is that these things oscillate a whole bunch of times before they decay. All right? Because if I'm talking part per million and I have a nice sharp resonance with a few ppm bandwidth, actually less than a few ppm bandwidth, fractions of a part per million, but that's a really long-lived oscillation, right? And that presents a measurement problem. Because if I am digitizing, so if this lives over, let's just say we go 0.1 part per million, then that means we need to go out 10 to the 7 oscillations. Right? If the width of the peak is 0.1 part per million, and we have this delta t, delta nu relationship, to get that resolution, we need to go out 10 to the 7 oscillations. And if you have something that's oscillating at 800 megahertz, and it's going through 10 to the 7 oscillations before you can do your Fourier transform, it turns out that's a lot of data to Fourier transform. Do you think MathCAD struggles right now with an FFT of a 4,000 element data point? Put in 10 billion? Is that right? 10 million. And it's not going to like you. And so we have a big challenge here. If we were just to straight up digitize that, and the fact at 800 megahertz, Nyquist says we have to sample at 1.6 gigasamples per second. Right? So that's some really fast electronics that you're then streaming out for very long periods of time. It's not efficient. Not efficient to do so. So what do we do? Well, we end the show. I need more pages. We're not going to end the show completely. The show must go on. I have 3 more minutes. I'm going to use them. Okay. You can do it. How did it move that there? And why is it not? There we go. Oh, there we go. I put it back. It's NMR, not FTR. Okay. So what we do is we take our signal. And we mix it back with more 800 megahertz. And we get something at 1.6 gigahertz and something at small delta F. Just like your car radio. You're mixing down from the 800 carrier frequency to an audio range. In a car radio, we're just doing the exact same thing here to get it into an RF frequency that is much more manageable in terms of the digitization.
What does it say under the bottom?
It says 800 megahertz plus delta F on the top. That's your signal is your delta F. And pure tone. So that's monochromatic. There's only one more small minor point I want to make. If the entire range of your spectrum is roughly, let's say 10 part per million. I don't know, is that reasonable? I don't do NMR. Sure. All right. It's a nice factor of 10, which makes it easy. That's why I'm choosing it, even if it's wrong. We're going to go with it, okay? All right, so the spectral range is, let's say it's 10 part per million. How short do I need to make my pulse to excite everything in this bandwidth? At 800 megahertz. Delta T, delta nu greater than 1, right? My delta nu is 10 part per million, and that is in actual frequency, it's going to be 10 times 10 to the minus 6 times 800 megahertz is my actual bandwidth, which would be 8,000 hertz. Yeah, because 10 to the minus 6 times 10 to the 6. So it's really 10 times 800, which gives us 8 kilohertz. So what does that correspond to in terms of time? If it was 10 kilohertz, just to make things nice and easy, then that would be 10 to the minus 4 seconds. So delta T, roughly 10 to the minus 4 seconds. In other words, if I have a pulse that exists for 10 to the minus 4 seconds, If I can take my pure tone and then chop it into a window that's only present for 10 to the minus 4 seconds, that simple act of truncation necessarily gives me the bandwidth I need to excite everything in the spectrum. Right? Delta T, delta nu. That simple act of truncation. This is where Fourier transforms help, where otherwise you wouldn't even think they would. Right? So if you turn on and off, find a way to rapidly gate the RF frequency going into your sample, then you've got the bandwidth needed for excitation. What is that excitation going to look like in the frequency domain? A sink, because we have a rectangle in time. And it turns out that it's actually much easier to make what you would really love is a rectangle in frequency, right? Just turn a nice turn on and turn off over whatever range you want and don't worry about everything else. But it turns out that logistically it's far easier to generate the rectangle in time. So that induces the sink in frequency, and we just live with it. Okay, I think I should just go ahead and stop there. I hope this has been interesting. And we'll say something about the end of the semester when everyone turns in their exam in 7 minutes. Oh, I should also point out, I think grand total of 6 of you have turned in online evaluations. Now that the stress of exam 3 is done and you're feeling good about your accomplishments, now is a perfect time to complete your evaluation for the course.